Okay, so let's go back and review. We talked about thermistors, photoresistors, Hall effect, ultrasonic, and piezoelectric, right? I don't think the book talks about piezoresistive. So everybody okay with thermistors? Yes or no? Huh? You okay? And then, of course, the biggest problem we have with thermistors is that but what do they change? They change their resistance with temperature. We have two types. We have a PTC and an NTC. What does that mean? What is a PTC? Now with pressure, temperature. Then an NTC, which is what I showed y'all, the resistance actually goes down with temperature. And that's all we have here, by the way, guys. Talked about photoresistors, commercially known as photocells. So these are photoresistors. So what do? Yeah, varies its resistance with light. These are all negative, which means when they see light, their resistance goes down. Look at the Wheatstone Bridge. Everybody okay there? So almost, not all, most of the sensors that change their resistance, we utilize a Wheatstone Bridge because it gives us the ability to balance it, right? You understand? Set a reference point. Talked about photovoltaic cells. These are commercially known as solar cells. Are you okay there? What do these guys do? They don't store energy. They produce. They don't produce energy. We can't produce energy, right? All we can do is change its form. So what these do is this takes light energy and converts it over to electrical energy or voltage and current. And of course, the amount of EMF or the amount of power it puts out is determined by the amount of light that strikes the surface. We've got, I think I told you we got lights around our front deck, and they charge batteries during the day. And on real shiny lights, those things stay on till 1 o'clock in the morning. On a day like today, they'll probably be off when I go home. Because why? There didn't enough light to absorb it. Talk about the Hall effect. Everybody okay there? These guys are electronic devices, by the way. And these sense the presence of a magnetic field. Or they can sense the amount of a magnetic field. I think I showed y'all a digital type, which we either turned on or turned off, right? And then an analog type where we actually could vary the voltage. And that was pretty neat. I don't know if somebody noticed it, but if we put one polarity on it, the voltage went up. If we put the other polarity, it went down. So it put out, I think, about 1.5 volts. Ultrasonic sensors, these are actually electronic circuits. So these are not standalone sensors. They're combined, they have to be combined with electronics, right? You understand? So these guys have his two parts. We call them transceivers. You know what transceivers mean? What does it sound like? It means it has the transmitter and the receiver in the same unit. So that's ultraviolet. We've got one with the Lego robot. I don't know if I showed y'all that. Did I show y'all that? I'll get one. The robotics course, you'll get to play around with those things. But this is the ultrasonic sensor. What's so neat, it looks like eyes. But one of them's a transmitter and one of them's a receiver. And what it does, it sends out light pulses. And then what does it do? So it sends out light pulse, and then what does it do? No, I don't tell the robot to do anything. It's a sensor. It's a sensor. It's like me saying my hands tells my eyes what to do. That's not true. So my hand touch is a sensor, right? You understand? So sensors don't do anything but sense. Okay, so yeah, but what does it do? It sends out a pulse. It's a distance sensor or a presence sensor. So it's a transceiver. So what does it do? Well, it sends out a light pulse, and then it sees how long for. So when sound hits something, what does it do? It bounces off, right? You understand? Understand? So if I can send out a pulse and I know how fast sound travels, and I can time how long it takes to get back, then I can use that to make measurements. I can use to see if something's there or not there, right, within a certain range. So that's the way ultrasonics do. This guy here has these are portals into the computer right here. These are I/O ports, which means these control input-output devices. These down here are sensor ports. So what I'll do is I'll come up here and hook my ultrasonic sensor up. And of course, it has some built-in programs. I'm gonna hook it up to port 3. And then what I'm gonna do is I'm gonna come over here, and then it's got some built-in programs in it. They got one called View. So what we're going to do is we're going to view the output of the sensor. And then it says to me what sensor. So we have a sound sensor, we have a light sensor, we have a temperature sensor it supports, we have a motor rotation sensor. Then this is our ultrasonic sensor. And I'm going to select that. And it's on port 3. So I'm going to say I got it on port 3. And what it's doing is I'm going to come over here and just point it at something. And what's it measuring? It's measuring distance. Well, how is it measuring distance? It's shooting out a sound wave, right? You understand? And then what? Time of how long it takes to come back. Some of these you can actually hear them click like that when they're actually transitioning. You can't hear it. Okay. So this is the ultrasonic sensor. What can we use this for? Huh? What do we use these for? Nobody knows? Radar gun works off the same principle, but it's in a, we can use a rangefinder for range finding. We use it to measure distance, right? You understand that? We can see if something's at a certain distance. So what we do on our robots is we program them to say, even though this is what we call an analog sensor, so it gives us a constant output. But what we can do is we can take that into something we call an analog to digital converter, which will take that information and convert it over to something the computer can use. So with this thing, you can do a lot of neat stuff. This is one of the robots that I built. And it'll just roll around forever. And it looks like it's smart. It looks like it's smart, but it's not. But what it does is it goes from the sensor to the customer. It stops. And what the program does, turns the ultrasonic sensor to a different direction. It determines the program determines which way it's considered path. That's the way it's decided. It becomes very popular on automobiles now. We have cars that auto stop. We have cars that my wife comes up and do something back over. We didn't have one side transmitter, one side. these are electronic. This is not a standalone sensor like photo resistor or something like that, right? You have to combine these things along with a pretty complicated electronic circuit. But yeah, radar guns, they work on the same principle, but they're a lot higher frequency. Radar, I don't remember the band. So we have ultrasonics, we have, but they work on the same principle. Submarines use sonar. Piezo-resistive, I don't think the book talks about these. These are solid-state sensors that sense pressure. And so we have pressure switches. We have analog pressure sensors that actually sense pressure. We have digital pressure sensors that tell us when to get up to a certain pressure or below a certain pressure. You got a compressor, you have one of these switches on there, right? Where it will turn on and build up to a certain pressure, and then once it gets up to that pressure, it will cut off until it won't drops down to a certain pressure. That's a compressor. So here's the pressure switch off on another circuit. That I have. This is two pressure sensors on this. Trips at 100 psi and 70 psi, which is pretty standard for compressors. In fact, that looks a lot like the one that's up here, doesn't it? That's about all they talk about in chapter 8. And what we're going to do now is move into chapter 15, which deals with photoelectric transducers or sensors. So we'll be looking at LED, light emitting diodes. We'll be looking at liquid crystal, which is covered in your book. We'll be looking at photodiodes. We've already looked at photoresistors. I got a little ahead of myself. Photoresistors. Photovoltaic cells, we've already looked at that, so we'll just skip over those. Photoelectric transducers, and we'll look at some of the most popular photoelectric transducers. And then some other things that the book talks about, we'll just touch on briefly because some of them we're not really ready for. Everybody okay? So light. What is light? What is light? Well, you can say light is energy. Light is a form of energy, but you can't say it is energy, right? We got all types of energy, which we cannot produce. All we can do is take energy and change its form, right? You understand that? So all the energy that's ever been produced is already here. So light, we can change its form. It's an energy source that we can change its form. But what is light? It's exactly right. It's an electromagnetic wave. Just like radio, just like AC on Alabama Power right there. It's an electromagnetic wave. But it's at extremely high frequency. And then, of course, this is what we see. We have the ability to see these electromagnetic waves. We see it's what we call as light. Light basically deals with frequencies that are in a certain range. We call it the spectrum or light or a light spectrum. And there's a lot of light inside that spectrum that we cannot see. It's not even visible to us, but it is visible to other things, right? So light frequencies between 1 times 10 to the 14th to slightly 1 times 10 to the 15 hertz. That's a lot of zeros, people. And this is up into what we call the terahertz range. Of that range, visible light is from 4.29 times 10 to the 14th up to 7.5 times 10 to the 14th power. So we're seeing just a very, very narrow range. And as example, so FM is a electromagnetic wave, but it doesn't produce enough energy for us to see them, right? You understand that? So your FM radio goes between 88 megahertz up to 108 megahertz. Are we okay? So this is electromagnetic waves. So we have radio, we have microwave, we have infrared, we have visible, then we have ultraviolet, then we have X-rays, and then we have what's called gamma rays. And then of course this doesn't go all the way down to low frequencies and ultra low frequencies, right? You understand where? So sound waves are the same thing that we can actually, these are electromagnetic waves that we can pick up, right? So here's the light spectrum. By the way, when you got something that moves, so, you know, I've got the ocean coming in, it's coming in at frequencies. Well, or we have what we call the distance between the peaks. So I'm sending something through something and it's changing. We have what we refer to as a wavelength, right? You understand? So these, I should have took that off. These are the wavelengths we use for fiber optic cable. But we can't see infrared and we can't see ultraviolet. So we use a lot of infrared. We use very little ultraviolet. And why is that? Why is that? Huh? We don't use very much ultraviolet. Why is that? Huh? You can't see it, and it's dangerous stuff. Ultraviolet's dangerous stuff. Ultraviolet will burn you. So it's the ultraviolet rays in the sun that burns you, right? Not the infrared, the ultraviolet. So if I'm using light that we can't see, then odds are it's not going to be ultraviolet, it's going to be what? Infrared. I don't know of anything that uses ultraviolet. So this right here, this is light. Can y'all see this? I don't have it on right now. I don't want to turn my projector off. Can y'all see that? Y'all can see that? Huh? You can see that? Huh? Some cameras that have auto that auto adjust, you can see it in the light. We had one around here that used to do it. This one right here, this right here won't pick it up. But yeah, some cameras will see ultraviolet light, but your eyes can't see them because they can pick it up at a different wavelength, right? So light that we don't see is infrared. Then we move up the spectrum, and depending on the frequency of the electromagnetic wave, depends on what color we see. So what do we see? So this shirt right here is green. Not red. I'll be red for something. Green is one of those colors that people have problems with. Red is red, blues. People that are colorblind. So this is what you're seeing is you're seeing what light my shirt reflects, right? So I'm getting all these colors, but the material and the dye that this is made of it reflects the green light. So you're seeing reflected light. Very high frequency is usually given in wavelength instead of hertz. So normally when we talk about light, they usually talk about nanometers. So most of the light is up in the nanometer. Huh? I just put them in there just before y'all came in. What I did is when I started looking at the book, this was covered in the book. So I thought I should add this in there. It's in the book. Might not be in the slides, but it's in the book. So this came off another PowerPoint that we use. We use this in a course called Cable Splicing and Installation, which we offer in the T2, by the way. This is where we teach fiber optics. If you're ever interested in fiber optics cable, that would be a good class today. It's a half-half, so the first 4 weeks we teach copper, how to splice, terminate copper wire. And then the second 4 weeks we teach fiber optics. And we teach the glass. We show y'all plastic. And we'll teach the glass, how to terminate it, how to splice it. So I have plenty of room in the class, by the way. It's one of those classes that they let me teach. Because I got so much power up here. Right now, I think there's only 4 people in the class. So it'd be a good class if y'all can take it during the day. So wavelengths, and we're not going to look at this. There's a formula for wavelength. I think that's given next. So wavelength. By the way, lambda is the unit of wavelength, and it's c, which is the speed of light, and then divided by the frequency times 10. That's the way they calculate the wavelength. And these are just different wavelengths that we have. Different ranges of wavelengths that have been specified. So a lot of these are specified by what we call FCC. You've ever heard of that, Federal Communications? And when we start sending stuff through the air, used to it was just random, and everybody would interfere with everybody. So what they decided to do, and it didn't take them long to do that, where they could start controlling this airspace. So now we control it and say, okay, you can operate within this frequency. And if you get above so much power, you got to be licensed, and we're going to monitor you. So there are some bands that are not monitored anymore. The old Citizens band was extremely popular before cell phones. And everybody had a CD. Well, used to you had to have a license when they first came out, but they opened up that range of frequency. They opened that up to anybody, so you can get a CD. It's just that only if your radio didn't put out over like 4 watts of power. If you went over 4 watts of power, you couldn't operate within the city band. And that's the way they kept everybody from bleeding over it. But here's your bands right here, guys. So ELF, VF, VLF, LF, MF, HF, VHF. Y'all have heard of that. That's a range of frequency that they assign to TV, to a high frequency TV. UHF, SHF, EHF, then we get into infrared light, infrared visible, ultraviolet, X-ray, gamma rays, and gamma rays are extremely dangerous. But this is just a range of spectrum. I don't have the channels right here. Of course, it's really nice on your radio, so if you're on FM, you're actually looking at the frequency range of the FM band. And what does it go from 108 megahertz down to something? And then the FM band, on the AM, if you put it on AM, you see the range of those frequencies. You see those, right? Your TV, for some reason, they decided not to give you the frequency. They decided to assign it a number. And what you need to do to find those, you'd have to look up those frequency charts. It says channel 103 is equal to this frequency. So everybody's okay here, right? We have hertz, kilohertz, megahertz, gigahertz, terahertz, petahertz, and exahertz. So your light spectrum is up in here in the 14th. So between terahertz, most of them in the 14th, so they're up in the terahertz. Huh? Well, no. Used to you could, because everything was done analog. And what they would do, what we do, and we don't have time to get into this class, but what we have the ability to do is we have the ability to set up what we call a tuned circuit. So what we do to transmit information is we impose that, we superimpose it on another frequency we call a carrier. So on your FM radio, that's what you're looking at. You're looking at the frequency of the carrier. So what that gives us the ability to do is to tune in a carrier. And then your radio, when it comes in, it uses filter to strip the carrier off and then pass the information on. Well, that was before digital. Well, digital, what they do is they encode all that stuff. So used to, you could get a filter when cable TV first came out. What they would do is they would put another carrier on that thing, which was different from the carrier, and your TV couldn't pick it up because it was on a secondary carrier, right? That changed the frequency. And so you could get a filter and you could put it on there and it would filter out that sub carrier. Now you could pick it up. And we could figure those out. It was real easy to figure that out. But that was before digital. Now what do they do when they digital? Not only do they put it on a carrier, but they encode information on that sucker. So if you don't have the key, you can't break it. Used to, you could pick up cell phones. We used to modify emergency scanners to pick up cell phones. The cell phones that's all they were. And it wasn't very hard to do. So we could pick up people's conversations all day long. But now it's all encrypted. It's all encoded. So that's one thing about sending information digitally is you can put little numbers in it. Now you have to remember, when I was a little tiny kid, everybody had what we call party lines. So you shared your phone line with probably 10 different people. Yeah. And you had a unique ring. And so your phone rang a unique ring. And what you do is you go up there and before you picked it up, you pick up the receiver and see if anybody was on there. And if there was, you cup it over and you listen to them. By the way, Ethernet works the same way. We call it carrier sense multiple access signal detection. So that's the way these computers work. Before they come online, they'll listen to the line. If nobody's on there, they'll come off. If somebody's on there, will come off. If nobody's on there, they'll sit down. Ethernet works the same way. Wi-Fi works that same way. Party lines. So what they talk about is, and I didn't have time to put this in the video, but another thing they talk about is some light. They give you some terms. But what I thought I'd do is we have a really good video on this. I think I'll show y'all this. And they talk about refraction, reflection. They talk about critical angles, and this is the way fiber optics works, guys. And they do this. It's really, really neat. Fraction. This is a piece of, we have two categories, well, we got a lot of different types. This is called plastic fiber. And the way it's set up, we're not going to, the book talks about it a little bit. But what we do, plastic fiber is only good for like 100 days. So we use it a lot in industry because it's very, very rugged and very, very cheap. The other type of fiber optic cable we have is made out of glass. It's extremely small. We talk about in microns. Standard conductor size, the actual one that carries the light is like 125 microns. It's very, very small. And a lot of people think glass, we don't see glass as extremely thin layers, right? So I use the analogy about aluminum. If I had a chunk of aluminum that thick, I couldn't bend it, or even that thick. But I can take aluminum foil and do in one because it's so thin. So I can break some glass fiber out here and let you look at it. But the glass is so thin that it'll do what? It'll bend. So you got to protect it a lot more than you do plastic. But what I want to do, see how this thing is curled up? What I want you to do when I pass it around is just look at one again and just move it and hold it up at the light, and you'll see the light moves through it. And it moves through it by something called total internal deflection. So as long as we don't exceed an angle, so notice when they was at a certain angle, it refracted out the side. But as soon as you got it to a certain angle, we call it the critical angle. As long as you operate it below the critical angle, you'll get total internal deflection. If you operate it above the critical angle, then you start getting refraction and you'll get loss in the cable. So that's why these guys here have what we call a bend radius. If you bend them too much. In fact, one of the labs we do, we literally measure the power transfer to the light power transfer, and we bend it up and we'll see it drop down. Of course, if you bend glass fiber too much, it will break. So that's the only big problem. We're talking about billions of bits of information we can send with light. We're not sending power, we're just sending it with what? Light. But if we send it in light, we've got to have some way we can get it into light in the first place. And then we got to have some sensor that detects the light, right? And this is where we get into these photoelectric devices. Are we okay? So that's about all the book talks about. Then it gets into what we call LEDs. So this is one of our sources of light to transmit is light emitting diodes. So LED is an acronym for light emitting diode. When the holes and electrons combine at the junction of a forward bias diode, energy is released in the form of photons. Silicon and germanium release very few photons, and these semiconductors impede the release. So silicon and germanium is not used in light-emitting diodes. We use in other semiconductors. LEDs are primarily made out of doped gallium. So you'll have gallium phosphate, gallium arsenide. You'll have all different types of metal. Are we okay? So this is just a picture. This is not in your book. This is showing you what happened. What we have to do is we have to expose the junction, guys, so we can see the light. Contrary to popular belief, the color of the lens of the LED does not determine the color of the LED. The lens only enhances the color that's emitted by the doping. So we dope that gallium with different ways, and different doping processes emits different wavelengths of light, which is pretty neat. The color emitted is determined by what it's doped with. And one of the big things that took them so long to do, in fact, the guy, I need to get his name, he won the physics. What do they call those big awards? They give out to these people every year. But he won it for physics because he created the white LED. It took them years to get the white LED. Because normally these guys don't want to admit a color, but white is what? It's multiple colors, which is pretty interesting. He won the Nobel Prize for Physics because how long white LEDs been out? You know, for a long time they kept moving toward it, and you can still see some of the cheap ones. They're not really white; they're they're blue, right? You know what I'm saying? But the white ones, those are really, really neat now. Gallium arsenide creates light around 900 nanometers or infrared. Gallium arsenide phosphate about 660 nanometers, which is red. Gallium phosphate produces 560 nanometers, which we see as green. Gallium nitrate produces 430. Y'all remember? I don't have to remember all of it. Gallium arsenide phosphate. Gallium phosphate produces orange light. Gallium arsenide phosphate. Gallium phosphide 885 nanometers, which is yellow light. So the ones that have been around for years, red's been around for years, and green and yellow. It took them a long time to get a good blue. So blue LEDs hadn't been around that long. And then, of course, now we got all different types of shapes. By the way, these guys do not use silicon. So the VL, and we forward bias them to make them work. If we reverse bias them, they're going to cut off. Because there's only current flow through them is what we call leakage current, right? So to forward bias them, we have to have a lot of combining at the junction. So that means we're going to have to exceed what we call VL. For silicon, what's the assumed VL? What do we call it? What do we say it is for silicon? About what? About 7/10. Germanium's about 3/10. Gallium, all of them's over a vote. So all of them are over 1 vote. I mean, we turn these things are not intended to rectify. They are indicators, right? You understand? If I'm going to rectify them, I will not use an LED. Also, an LED has a fairly low reverse breakover voltage. So we're not going to use these to block a lot of AC. But we can trick it by putting a real diode either in series or parallel with it. I'll show you how to do that. So here it says, this guy right here, this is the color on the side, so this is 1.5 volts, 1.7 volts, 1.7 volts, 1.8, 2 votes, 2 votes, 2.2 votes, 2.1 volt, all the way up to pale white, cool white, and then into your other colors, all the way up to 3.8 volts. A rule of thumb for LEDs is 2 volts. If you do 2 volts, and when you size your resistor, odds are you're going to be okay. Unfortunately, a lot of our meters won't put out 2 volts to check these things. What did y'all get when y'all checked the LED? Y'all remember? Y'all did that lab last class? Anybody remember? 1.7, right? Did it light? Well, it all depends on the meter. That's why I like it Sperry. This Sperry puts out almost 3 volts on the diode scale. So here's my Sperry. Turn it on. And let's see, I can get it so y'all can read it. So this meter don't show us overload. It gives us the maximum voltage it'll put out on the ohm scale, which is about 3.12 volts. So this guy here will break down just about all LEDs. This LED right here is really, really neat. Normally an LED will have 1 leg on it. Notice this guy right here's got 4. So what I've got is, and by the way, on this one, the long lead identifies the cathode. And what I'm going to do is I'm going to come up here and touch it. So when I touch this lead, let's see if it shows up. Let me get it in the graph. This is a neat LED. So what they add is actually 3 in a row. So this displays, got to get the right meter. I got 3 meters up here. So this guy right here displays what color? Let's get it in front. Can y'all see? So this is 1.8 volts, and it's what color? Red, right? And then this right here is, and this meter will act, this is what? Blue. And then this here is green. So this actually has 3 LEDs in one unit. Before I saw this one, we used to have what we call a tri-state LED, which was green and red. So if you put one polarity on it, it would go green. The other one, it would go red. And if you put an AC on it, it would go yellow, which is pretty good. But this meter right here, the Sperry will turn it on. This meter over here, the meter man, the WaveTech, it'll check them, but it'll turn on one of them. So it's up to your meter if it puts out enough current to turn them on. But most of them will show you pretty good the VL. So y'all's was I think we had some green ones in there. I think we had some red ones, and I think around 1.8. But if you use about 2 volts when you calculate these things, you should be okay. Are we okay? Rule of thumb. But if you're really particular, then you'll probably need to look it up on the data sheet. If you get the data sheet, there's LEDs all over the place. So this is the symbol for a light emitting diode. It's basically the same symbol as our regular diode, except it's got arrows pointing it. This is the official symbol, by the way, but 99% of the time, you're not going to see the circle. So notice the arrows point out, which indicates, so when we see arrows pointing out, two arrows pointing out, it means these guys are going to emit light. If we see the arrows pointing in, it means they're going to detect light, right? That makes sense? Okay? So this is symbol for an LED. How do we do? We turn these things on with what? We have to forward bias them. And we turn them off, we reverse bias them. Huh? This is the symbol for a light emitting diode. Like I said, most of the time you'll see it without a circle. Sometimes you see it without the arrows, but it's going to be in a device that you know is like a 7-second display. A lot of times they'll go without the arrows because the LEDs are so close together. They can't put the arrows on each one. Are we okay? So we use these things all over the place. These are called 7-second displays. We'll look at later on. We use these all over the place to display numbers and some characters. These are LEDs, by the way. Y'all know that? These big old things they have on the side of the road, there's nothing but LEDs. Just thousands of LEDs. Using the prime colors. What's the only colors our eyes can see? Well, your eyes can only see 3 colors. What's 3 colors? Red, green, and blue. And then you can see what we call shades of gray or black. But it's not really black, it's shades of gray. So between those 4, then I can see any color. Just those 4 colors, right? Understand? So what we can do is we can combine those things on these units. In fact, this is one right here. So this is what they are. They're made up of red, green, blue. Can y'all see them on a black background? So red, green, blue on a black background, what can I do? I can display almost any color. I'll pause it. Well, no, y'all can pass it. Y'all got your display on? Probably better to come up here. Try to move this across white and blue, and what I want you to do is come up here and just look at this. Let me pause it. A lot of people led by white light, so that's the difference between. So we talk about these are all what we call flat screen displays, okay? But now we group them into LCDs and LEDs. Well, they're all LCDs. It's just an LED. The one they call the LED is backlit by a fluorescent bulb, and then the LEDs are backlit by light emitting diodes, white light emitting diodes. But they're still run on the principle of liquid crystal. So what we have to do, by the way, when we put these LEDs in there, normally we're going to put it across a DC voltage. We can put them across an AC voltage, but we got to be real careful because the reverse breakover is very, very low. So what we do is we'll come up here, and depending on the voltage we put across them, we're going to put a series drop-in resistor in series with them. So the way we would do to forward bias them, if this is DC, is I'll come over here and I'll put the anode toward the positive and the cathode toward the negative. And then we're going to have a series drop-in resistor either in the cathode or the anode. Didn't make any difference. And we calculate the size of that resistor. So what do we need to know to calculate the size of a resistor? R is equal to what? What's R equal to? Huh? That's something you need to know. Huh? No. Huh? The only times that we have is voltage, right? V is equal to I times R. All the rest of them is divided. So is R is equal to V over I. So I need to know two things. On the LED, I would need to know the VF, and then I would need to know the IF. And we never operate them at their maximum current. So if I've got a data sheet, I can look this up. One of the things it shows us is the maximum current. So you notice just about every one of these are what? 20 milliamps. So usually we operate them anywhere between 10 and 15 milliamps. We don't want to operate them wide open. So rule of thumb is 2 volts at 10 to 15 milliamps. What you do is you choose, because we have to go to a standard resistor, right? You understand that? So if I calculate a 132 ohm resistor, there's no such thing as a 132 ohm resistor. So we'd have to choose from the standard value. So let's say this guy's got a VF of 2 volts. What size resistor? And let's say this is 5 volts. This has got a 2 volts. What size resistor would I use? And of course for IF we're going to use what? Let's use 15 milliamps. And then we'll round our resistor down. Or you could probably use 20 milliamps, but I always do what? You use 20 milliamps, always round down. I don't care if it comes up to be if it comes up to be on top of a resistor, you would round it down. So how much voltage would the resistor drop? Kirchhoff's voltage law says the sums of the voltage drops in a series loops have to equal to the applied voltage. I have 5 volts applied, my diode's dropping 2 volts, so how much does the resistor have to drop? 3. Pretty simple. So I'm going to say R is equal to 3 volts divided by 15 milliamps. And what we got? Huh? Everybody okay? Pretty standard for these is a 330 ohm resistor. That's pretty much what most, if we run it on a 5 volt supply, that's really standard. But we could use a 270. That's a legal value, right? You understand? The closer you get, the more current you put through them, the more light they produce. But the closer you run them to their maximum, that's the maximum. So the closer, if you run them at their maximum, they're not going to last as long, right? You understand that? We don't like to run things at their maximum rating all the time because that's their maximum rating. Okay. So if you're going to operate this, and we could operate this on 120 volts AC, but what we'd have to do is we'd have to come over here. We could do this. We could put a regular diode in series with it. And we'd make sure the reverse breakover voltage was greater than peak, right? You understand that? And then I could come over here and put my LED. And then I would calculate a resistor to drop half of, would drop, what would it drop? This would be considered a half-wave rectifier now, right? You understand? Yes or no? So we would calculate the average voltage. Another circuit I saw that was pretty interesting is where they came over here and they put the diode in parallel. And I'd never seen this before, but here's our LED. And then what we would do is we would take a diode and we would put it like this. So when it's reverse biased, that's not right, is it? Yeah, so when it's reverse biased, it would bypass the LED, but you're still gonna have to have your series dropping resistor, right? So I saw on one circuit when they did it this way. This is the way I always did it right there. You just put a regular diode in series that has a breakover voltage that will meet the requirements of your circuit, and then you calculate the resistor for both of them. And this way we can run them in. We could run them in an AC circuit. We could run them in just about any voltage that we needed. Are we okay? So we can arrange these things all different ways. These are called 7-segment displays. Can y'all see how they work? So what can I do with these? So if I came over and turned this one on, and I 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 turned this one on, what would I see? I see the 3, right? You understand that? If I came over here and turned this one on, and this one on, and this one on, and this one on, and this one on, what would I see? 2, right? Of course, if I came over and turned this one on, and this one on, and this one on, and this one on, and this one on, I would see a what? 5. So I could do a 6. I could do any number. I have no problem doing any number. So this is not a LED. These are liquid crystal. That's the way your meters work. Your meters use 7-segment display. I had somebody tell me that they'd never seen these. But see, these are 7-segment displays. Can y'all see the segments? But they're not LEDs. They're liquid crystal, but they work on exactly the same principle. Exactly the same principle. So using those 7 segments, I can do what? I can display any number. We can display some letters too. But so see, here's some letters. So this is still a 7-segment display. And of course, this says overload. And normally they include a decimal point. So there's 8 segments. There's usually 8 LEDs in there, but 7 of them are used to control the numbers. And then normally you'll get another one that is labeled what? Decimal point. You see why they're called 7-segment displays? We have 2 types. We have what we call common anode and common cathode. So you can see this is common anode. So what we would do is we would take this right here. We got 2 options. We can come over here and we can put a resistor right there and connect it to a plus voltage. And then what we'll do is we'll turn it on with common, right? This is not the preferred method because the more LEDs you turn on, now you got a parallel circuit. And every time you turn on an LED, then this resistor would have to conduct the current of 2 LEDs or 3 LEDs or 7 LEDs. So what happens is that the more segments you turn on, the dimmer your display will get. So the preferred method to turn these things on is to connect this guy directly to your power source, say +5, and then what we do is we'll put a resistor in series with each segment lead. And then we would put our common over here. So somehow we're going to switch this to common. So if I switch that to common, this guy here is going to forward bias and it's going to turn on. So we have to control each segment individually, right? Understand? We have special ICs that do it for us. If you understand binary, we have what we call a BCD, the 7-segment decoder IC that you put in a binary number and it'll display, it'll decode it for you. But these are a little more these are fairly complicated to control, but they'll display for us. Like I said, your meter uses 7-segment displays, except they use LCD instead of LED. This is common cathode. So you got to know which one you got to replace it with the same one, right? You understand that? Does that make sense? I didn't bring any of these out, guys. Let me this is what's so neat. You know, those big old things are nothing but basically computer monitors. And a lot of times they're just running a PowerPoint. That's all they're doing. So they're just big versions of these. But instead of these having these little old tiny dots, they're using those LEDs, right? Understand, to form the triads. These have a limited range of what you can do. We can't do many letters. I can do an uppercase A, I can do a lowercase b, I can do a C, I can do a lowercase d. I can't do an uppercase D because it looks like a 0, right? You understand? I can do something that looks like a T, but I can't do all these letters. These are star LED 7 set. These are 1, 2, 3, 4, 5, 6. These are about 12 or 15 segments. But these guys right here, you can display just about anything. And we calculated the resistor. Are we okay? So this is what we looked at. Generically, if you don't have the data sheet for these things, you use watt per VF, 2 volts and 15 milliamps, and you won't run into any problem. If it don't come up to be bright, you get these that put out that drop 3 volts. You know, you might decide to go to a smaller resistor, but this will give you a starting point. Triad, this is a group of red, green, and blue elements. Black is understood. Pixel is triads controlled as a unit. All the triads in a pixel will be the same color. Pixel resolution is the size of the pixel, which determines the shape of the display unit. So that's what you do when you let's see if I can get here. So screen resolution. So that's what you're doing right there. You're adjusting. You're not changing the size of the triad. You're changing the size of the pixels. That makes sense? You understand that? So what's a pixel? A pixel is a group of triads that's controlled as one color. And you can't get your pixel resolution on your monitor cannot be smaller than your triads. If you ever do, that's why every time you change it, it'll come up here and say, is it okay, right? Can you see this? And what does it do? So if I change my pixel resolution, it'll pop a screen up there and it says, if I can't see anything, it'll revert back to the old one automatically. Used to it wouldn't do that. And this was back in the days where we could get into the configuration files, and if we screwed up, we would literally have to go into the configuration files and change the resolution that way. But now they realize a lot of people try to do that, so what do? If I change the pixel resolution that this monitor won't do, I don't know if it'll do that one or not. And then I'd say, okay. If it don't do it, then it automatically will do what? It'll go back to the old one after a certain amount of time if I don't say okay. Now this monitor right here will do it. Of course, I knew it would because this was made as a match set. When you got a desktop computer and you go out and buy a new monitor, your video circuitry might support a higher resolution than your monitor will do. So that's why they decided to do that. They got people all the time. They would try those high pixel resolutions, and they'd try them, and their screen would go blank or it'd go all crazy on them. I'm going to tell you how many of those things I had to do. But nothing wasn't wrong. It was just them doing it. Well, everybody's seen these things. Those things are really neat. Sometimes if they get them close enough, you can actually see the dots up there. A photodiode. This is one of our first sensors. So an LED is not a sensor, but it could be part of a sensor, right? You understand? Especially for diodes whose leakage current is controlled by the amount of light striking the P-N junction. We place these things in the circuit, what? Reverse bias. So what we're going to do here is we're going to let the light control the leakage current. So first of all, these guys are going to have a lens on them. And we're going to put these in their reverse bias, and when we expose the light, their reverse current is going to increase. When we take the light away, it's going to decrease. So we'll have to hook these up similar to the way we do we'll have to use a resistor, guys. They don't use one here. So normally the symbol, here they're using the symbol of lambda, but most often you'll see the symbol like this. So what they'll do is instead of having the arrows going out, they'll have the arrows what? Pointing in. These are called photodiodes. These guys are still used, but normally we use a thing called a phototransistor, which works the same way. So you think about it, I got this thing right here, it emits light. Over here it's got to have what? Got to have something that senses light. So we could use photodiodes. Most of the time they use phototransistors because they operate a lot faster. But this is one of the devices that were originally used in remote control. So you don't run into photodiodes much anymore because they've been replaced by phototransistors. Typical diode circuit, basically almost the same as a Zener, so we'd have to use a watt resistor in series with it. Are we okay? Yay, nay? These are some of the other diodes that we talk about in the book. A PIN diode, photoelectric devices. A PIN diode. This is a variation of a photodiode. But what they do is when they make it, they have a P, they have an N, and then they have an intrinsic section in there. So that's how it got its name. What's intrinsic? What's an intrinsic semiconductor? When you got that on, by the way, I did finally get the test 1 graded. That was interesting. What does intrinsic mean? So here we're running into that term and nobody knows what it means, even though it was on the test. I think we have our second test week after next, right? I know it's coming up. Usually the week after, huh? Next Tuesday? Might be. What's intrinsic? So intrinsic means pure, it's undoped. So we put a section of undoped semiconductor in the center, and then we go back to the outside P and N. These guys, I'm not sure, I'd have to do a little more research, but we do the same thing. These guys detect light. I'm not sure exactly which one we have. I'll have to look and see. We've talked a little bit about transistors. So transistors are devices that give us a current gain, right? You understand that? And basically, if you understand one of these, you understand a transistor. What's the symbol for? What's that a symbol for? That's not a symbol for potentiometer. You're close. Here's a symbol. Here's a symbol of a potentiometer. It's got this thing coming in the side. Now this is a symbol for a rheostat. A rheostat is a variable, it's a true variable resistor. We use a rheostat to control a current. It works like a resistor. We use a potentiometer to control the voltage. We can make a potentiometer act like a rheostat by connecting. Now it acts like a rheostat. So we don't see many rheostats much anymore. Because here I got a unit now that serves two functions, and they cost about the same thing. But who turns this knob? Who turns that knob? Right. Well, a transistor, we use another device called a base that we electronically change the resistance between these two legs right here. We call this the collector. We call this the emitter. And that's representing this. And that right there is controlling that wiper right there. So what we do is we'll come in here and we put a real small current, maybe 1 milliamp. And over here, between there, it might turn that thing on to get 100 milliamps out. So what we get out of a transistor is we can get a real high what we call current gain. But here's the variable resistor right here, and that right there is the control. But instead of me manually going up there and turning that sucker, we can electronically control that. So we have a thing called a phototransistor, and what we do is we'll still draw the base, but we come up here and we do that. So what happened is the light is controlling the base. And these are called phototransistors. This is what's prominently used right now because we got some features on this that the base lead usually still comes out. It may be necessary. It might, but if the base lead comes out, we can do a lot of new stuff. The phototransistor, you're going to have to see. These are my phototransistors. These are phototransistors. They look like a regular LED, but they're not. These guys actually allow on these. I don't know what my phototransistors. A lot of times, also what we want to do is we want to do isolate. So my programmable logic controller, I got a PLC. These are computers. So they cost a pretty good deal of money. But I'm opening these things up in an industrial application, which has a bunch of stuff that can go wrong, right? What I don't want to do is I don't want to take my PLC and couple it of actually input stuff into it that could damage it. So normally the inputs on a PLC goes through something called an optical isolator or an optical coupler. So what we'll do is from the outside world, we'll come in and we'll put some protection circuit out here. And then we'll come over here and we'll bring this in through a light emitting diode. And then over here what we'll do is we'll have some type of photo detector. So right now we'll use a photo LED. So those guys right here, so my input is electrically isolated from my input of my PLC. So what my input is doing is turning on the and this is a little old square block. I mean it's just a little IC. Usually they got 6 or 4 pins. Or they might even have 4. So this is all I see. And then this circuit is inside of it. And what that does is it isolates my inputs from the inside of my computer, right? You understand that? And these are called optical couplers or optical isolators. We'll look at an optical interrupter in a minute. We have light activated SCRs and we have photo triacs, but we'll understand those when we talk about those in a later lecture. But they talk about them just a little bit in this chapter. Everybody okay? Okay, y'all take a break. This anyway, so we're going to go over there to the line and look at it. These are our photoelectric sensors. We have sensors fall into categories. And of course, the two main categories would be digital and analog. Y'all understand those? Okay, so you're okay with digital and analog. So what is a digital sensor? Well, it gives us 2 states, and it's usually a voltage, by the way. So digital, what we need to do when we say a sensor converts a physical stimuli into an electrical quantity, what two electrical quantities would be the easiest to sense? Even when I used even though I used a thermistor, I hooked it in series with a resistor and turned it into a voltage, right? So the main thing that we sense, we have 2 things we can sense. We can sense current, and we can sense voltage. And voltage is the primary method of sensors giving us information. Well, in controls, digital sensors are either going to give us a voltage or give us no voltage, right? You understand? And then that would be digital. So that way we can say yes, no, true, false, 0, 1, right? You understand that? Analog is going to give us a continuing varying output. So a while ago when I hooked up this is an ultrasonic sensor, and we looked at an output, but what it's doing is it's giving us a voltage that's proportional to that. So I don't know if you can hear this or not. So this is the program that's running now. So what it's doing is the program is taking that voltage and converting it over to a what? A sound. Well, what we need to do, so this is an analog sensor, but this is the digital computer. So what we need to do is we need to have something that we refer to as an analog to digital converter. We're not a room. Analog to digital converter. And we've got 2 types, but the one we'll look at over there, these are digital analog to digital converters. So what we do is we set a threshold. So if the analog output goes above this, it says it's true. If it drops below that threshold, we call it false. So we put a problem in the analog to digital converter over on our manufacturing line this morning, did we? Right. So what we can do is these are the different types of photoelectric. So these guys are analog sensors, but they have the digital A to D converter built into them. So from my point of view, these are digital sensors because I can't fix them. I can't do the A to D. Now most of them have a little old tiny set screw on it. You can just about see it right here. That usually gives you the ability to set what we call the sensitivity, so you can set the threshold on. And I'll show you that on our digital sensor over there. But these are the primary types of. Then we have what we call contact sensors and non-contact sensors. And all our photo sensors are non-contact sensors. By the way, in the trade we call them proximity sensors, but they don't make physical contact. As soon as you make physical contact, then you have friction. So contact sensors wear out over time, right? You understand that? Non-contact sensors, basically, they will just about last forever if you just take care of them and keep them clean. So this is the first one we'll look at. It's called a through the beam sensor. So what we do is we have a transmitter and a receiver on two different sides. And what we're trying to detect will come in and actually break the beam between the transmitter and receiver. So we understand the receiver. It's going to either be a photo transistor or a photodiode. Oh, wait. Here's the photo. I found the photo transistors. You can see these have lenses on them. They have 3 leads. So the receiver would be either a photo transistor or a photodiode, and then we have an LED on the other side. Well, that's what we're going to get into in a minute. So this is called a through the beam. A through the beam we'll have two. We'll have a transmitter and receiver. And what you do is you break the beam between the two. So this, a false, would be something in the way. So if this thing gave me back a true, it means something's not in the way. If it gives me back a false, it means it's in the way, right? You understand? What's that? Well, they have what they call light curtains, which work on the same way, where they'll put it's a through the beam, but it's a bunch of them. And they'll put a bunch of them on each side, and if you walk through or crawl through or something like that, they're going to pick you up. But all it is a through the beam. It's just that you got a bunch of them. And they call them light curtains. Then we have what we call retroreflective. What retroreflective? Now these guys have the ability to be the longest range because they're going to have a certain range. So let's say the range is 6 feet. Well, then I can space these things 6 feet apart. We had some out of U.S. Steel through the beam. Them suckers must have been 300 feet apart. They put them over on the where the line crew kept all their wire out there on the big old spools of wire. They had somebody come in there one night and took one of them big old spools and put it out the side of the fence there, and they hooked it up to their bumper on their car. And they'd roll that whole spool out and rolled it off on the side of the road. And they'd come back every once in a while and cut off chunks and take it in and sell it. So we did that. We ran a real thin wire up the chain link fence. So if anybody cut it, it would set off alarm. And then we put a big old through the beam sensor, and you couldn't see it. It was infrared. You couldn't see the light. So people didn't even know it was there. So if anybody tried to walk in there, they would trip that thing. This is called a retroreflective. Now these, what we do is we have the transmitter and receiver is in one unit. And we shoot the beam out and we hit a retroreflector over on the other side. Now a retroreflector is a reflector that tries to reflect back from where it came from. So a mirror is a reflector, but if I was off line just a little bit, I wouldn't pick it back up, all right? But a retroreflector, so stop signs have retroreflectors on them. So when you're you're off to the side, but yet you can see the still big wad up there. You can still see the big stop up there because that's a retroreflector. But it only works over a certain range. You get up there up beside them, you can't see anymore. People wear these vests that they put on, bicycle riders with that, those are retroreflectors. So they have a tendency to reflect back to the source, right? You understand? So what these do, these work similar to a through the beam. You still break the beam. So if the object breaks the beam, it's there. If something don't break the beam, it's not there. Okay, does that make sense? These guys don't work with transparent. We couldn't use these to sense glass, right? But we can use to sense most objects, especially if I can set the sensitivity on it. Then the last one we have is what we call the diffuse. A diffuse, the transmitter and the sensor is on both sides, but a diffuse is what our eyes are. Our eyes are a diffuse sensor. So what does our eyes depend on? They depend on reflected light off the object, right? You understand? So a retroreflector reflects off a reflector. What a diffuse sensor does, it shoots out a beam of light, and then it looks for reflected light. So that's exactly what our eyes do. It looks for reflected light. So these are the three primary optical sensors that we run into. What are they? Through the beam, retroreflective, and diffuse. Now we got two other solid state sensors that the book does not cover, but it's pretty important that we look at them. And I don't think they're even in the slides. Some of y'all's had AC, some of y'all haven't, but we've talked a little bit about AC. We got these devices called capacitors. In capacitors, what makes up a capacitor? Does anybody know? Anybody had AC? What is a capacitor made up of? Yeah, two metal conductors separated by a insulator. That technically we refer to that as a dielectric. And so they have different insulators they use. What determines the amount of capacitance? So all I got to do, I don't know where I put that slide at, but I'll find something I can write on. But all we have to do is separate those two. I think I got a blank slide back there somewhere. Yeah, right there. So all we have to do, have two conductors, then we separate them with an insulator. And this sets up a capacitor. So we get capacitors that we don't want. It's called stray capacitors, right? And then we got capacitors that we deliberately make because they got unique features that you'll learn about in AC. But what determines the amount of capacitance is the size of the plates, and then of course the insulator, what type, the dielectric of the insulating capabilities. They call it a dielectric constant. And it's rated to air. Dry air has a dielectric constant of 1, right? And then how close we can get the plates together. So what happens is these things electrostatically react to each other, which is pretty neat. So what we can do is we can come up here and we can set up a capacitor, a capacitive effect. It's not really effect like this. And then these guys will interact with each other. And then if we get a material in there, then we're changing the dielectric constant. We'll change the capacitance. What material can that be? Just about anything. So we have what we call capacitive sensors. A capacitive sensor will sense, we can make it sense liquids or solids, which work out pretty good. Then we have something called an inductor. So a capacitive sensor will sense liquids or solids. Then we have an inductor. So all this has AC. What determines inductance? So a capacitor stores the charge, but it does it electrostatically. We can use these things. So we can charge them up. So we keep them sometimes. So I've got a coffee pot at home. If the power fails and if it just blinks or something, that coffee pot don't lose anything because it's got a capacitor to keep charged up in there. And it's not a battery, it's just a capacitor. And then it does what? It discharges them, which is pretty good. We use them to create phase shifts. We use them in filters and all different types of things. But what we do here is we change the dielectric constant, we change the capacitance, which is sensed. Okay, y'all understand that? An inductor is nothing but a loop of wire wrapped around something. We could wrap it around air, or we could wrap it around some type of metal or ferrous material. So what determines the amount of inductance you have? These guys store a charge electromagnetically. They're really good. But what we can do here, what determines the amount of conductance, is how close you can get the coils together, the length of the coils, the number of coils, and what you wrap the thing around. Okay, so we call it the core. So what we can do with an inductor is we substitute something for the core. But the problem is that these things will only sense metals. So inductive sensors only sense metals. Capacitive sensors will sense liquids or solids. Capacitive sensors will sense glass, because that's a solid, right? You understand? So a passive sensor, we can set up to sense just about anything. So these are two solid state sensors that the book don't talk about, but they're used a lot. And then, of course, Hall effect senses magnetic fields, right? We okay? So these are all solid state sensors, and these are all proximity sensors. One of the sensors that we'll look at over there is called a limit switch. These are contact switch sensors. And when I show you those, it's going to be pretty obvious how those things work. Those are actually contact sensors. But these are just nothing but switches. But instead of me going there and flipping the switch, something flips the switch for us. Okay? Okay, so let's go ahead and pause.